In this video, we are going to discuss about variational principle. Using this technique, we can find a curve y is equal to y of x such that the integral of a function f, which is a function of y dot and x between x1 and x2 has a stationary value. Okay, so here remember one more thing, this y dot represents dy by dx. Okay, so now here you see, suppose we have this Cartesian coordinate system. So here you can see this is suppose x coordinate and this is y coordinate, and there are 2 points, this is one, another one is this, and this is given by x1 y1 and this is x2 comma y2, and the part we need to find is suppose this one y of x, and let us between these 2 points we may have many paths. So there is another part, neighboring part, suppose which is in red color, this is suppose eta of x, and the variation is scaled by alpha. So this alpha represents variation. Now at the end points, at the ends variation is 0. So that's why eta of x1 will be equal to eta of x2 is equal to 0. Okay, so here we can write integral of this function f from x1 to x2, f of y dot x dx. Okay, now if you differentiate this with respect to alpha, di by d alpha, then what you can have, this is x1 to x2, the derivative of the function f of y dot x dx. This implies, let me scroll down, from x1 to x2 del f by del y by del alpha plus del f by del y dot by del alpha plus del f by del x, then del x by del alpha. So it is clearly that del x and del x by del alpha, this is going to be equal to 0. So because here you can see this x doesn't depend on alpha, but these 2 remaining terms are non-zero, as y depends on alpha variation. Okay, y is the variation of alpha is the variation of y, so here dx. So this implies x1 to x2 del f by del y by del x dx, plus we can separately write integral from x1 to x2 del f by del y dot by del x dx. So we can write this way. Now the family of the neighboring paths from between these 2 points can be represented by this equation. So the paths, the set of paths between, this is di by d alpha. Okay, This is suppose equation number 1 between x1 and x2 can be represented as y x comma alpha is equal to small y of x comma 0, which is not a function of alpha, plus alpha eta x. This is suppose equation number 2. If you differentiate this equation with respect to alpha, then what you will get? Dy by d alpha. Then if you differentiate this y of x with respect to alpha, that's going to be equal to 0. So we have derivative of this alpha into eta of x. So here we can use the product rule. This is u and this is v, and derivative of u into v is u derivative of v plus v derivative of u. So use that rule. If you use that, you will get, let me scroll down, okay, alpha derivative of eta, that is represented by eta dot x, plus then eta of x derivative of alpha. So now derivative of alpha with respect to alpha, that's going to be equal to 1. So that's why simply we can write eta of x. Now remember one thing, eta is a function of x, so derivative of this function with respect to alpha will be equal to 0. So that's why we have only, let me write this way, dy by dx is equal to eta of x. So we have got this after differentiation. Okay, now this is suppose equation number 3. Now from 1 we can write di by d alpha, that is equal to x1 to x2 del f by del y, then del y by del alpha dx plus integration from x1 to x2 del f by del y dot, then del y dot by del alpha dx. Now you see the second part, this second term of this function of this equation 1. Here you see, here we are going to use this rule. That is integration from a to b u dv minus is equal to u into v from a to b minus integration a to b v du. If you use this, then you will get from this part only, you will get del f by del y dot, then del y by del alpha, okay, considering this one as dv, then here you will get v, isn't it? So this del y dot by del alpha becomes del y by del alpha here, and from x1 to x2 minus x1 to x2 integration x1 to x2 derivative with respect to x, then del f by del y dot, then del y by del alpha dx. Okay, so I hope you have understood this. Now here what we can do, here you can see del f by del y dot. So we have already got in equation number 3 that del y by del x is eta of x. So this can be replaced by eta x, eta of x. and x1 to x2 minus integration x1 to x2 d by dx del f by del y dot del y by del x dx. Now here you see at the endpoints, here you see at the endpoints this is eta x1 and eta x2, these two are equal to 0. That is why, so if you integrate this from x1 to x2, this value must be equal to 0. So now using this value here, so putting this here, what we will get, this from this we will get di by d alpha is equal to integration x1 to x2 within curly bracket del f by del y minus the d by dx of del f by del y dot bracket close then del y del x. So here you see, here we have taken this del y by del x common, isn't it? So now here you see this this part will be stationary when this will be equal to 0. This function to be stationary, okay, this part this part y of x will be stationary if di by d alpha is equal to 0. Okay. So here we can write this I is stationary, means del I, or you can say so let me write here di by d alpha is equal to 0, and if you use this value here, then what you will get? You will get integration from x1 to x2 within curly bracket del f by del y minus derivative with respect to x of del f by del y dash, and within bracket here we can replace this by eta of x. We know dy by dx del dy by dx is equal to eta of x, isn't it? So we can replace this by eta. So now eta dx. Okay. So since eta of x is an arbitrary function which vanishes at both endpoints, so as this we have already got that eta x1 is equal to eta of x2 is equal to 0. That is why we can write del f by del y minus d by dx of del f of del y dot is equal to 0. So this equation, here you see, this equation is known as Euler Lagrange equation. So hope you understood this, and if you are new to my channel, please subscribe the channel, help me to grow my channel. Thank you for watching, and in the next video we are going to solve some problems using this equation, Euler Lagrange equation. So it's very important. Okay.